sequence of non-stochastic numbers, we have just one limit. And that's very clear, but when things get rendered, you can distinguish between different kinds. The most strongest is convergence with probability 1, almost sure convergence, and we have a first law of large numbers. And the law of large numbers discusses the average of the number of random variables. And the one of Kolmogorov says if you have IID random variables, then the average of them converges almost surely to a number. Let's call it mu. If and only if that number is the expectation of one of these x's. And they are IID, they all have the same expectation, if it exists. This is a strong law of large numbers. Okay. Frequently we use a weaker concept of convergence and probability. That's formally defined here in 1 and 3, but we discussed it already last time. So I would say look at it at home carefully. Then we had also convergence in L2 or in quadratic mean, and here we say it briefly, if the expectation converges to mu of a sequence y1, y2, etc. And the variance converges to 0. Look here, I don't need to indicate here a p or an almost sure thing. I don't need that because this is not random. It's an expectation, so it's a number. And then we just have convergence as with random numbers. The same thing here. This is just a number, it's not a random variable. Variance is also a number. Converge to 0 without a p or an almost sure here, p almost sure. If you use it and you have a random thing, a sequence of random variables, and you put an arrow and you say this converges to beta, say, without an indicator, you lose a point. Because I don't know what you mean. I only know what you mean if the sequence is non-random. Then we know what an arrow is, what the meaning of an arrow is. And don't use an arrow in any other meaning. Because then you will lose points as well. Say we have done this, and now we go to the next point, you lose a point. Because this has a mathematical meaning. As the limit of a sequence of non-random numbers. Okay, we have relations between the different kinds of convergence. Almost sure convergence is stronger than weak convergence, at least, yes, than convergence in probability. And convergence in L2 or quadratic mean also implies convergence in probability. We won't prove them. In earlier classes where we spent much more attention to asymptotics, we did prove them. It's doable, but we won't spend time on it, otherwise we cannot go through all these chapters. Now, very powerful result, continuous mapping theorem. If you have a function and here yn is a scalar, but you may also think it is a vector. Of course, then the definition should be different from what we have over here, because here for convergence and probability we have an absolute value of a scalar random variable minus a number, but in more than one dimension this will just be the length of the vector, Euclidean length. And then you could say the same thing, and that is how you define convergence and probability for a vector. That the probability mass in a little sphere around the true value mu, or around the vector mu, that the probability mass then converges to 1. But okay, It's written down in scalar form. However, things become nice if you look at result 6 and the continuous mapping theorem. For example, if y consists of two elements, we have yn1 and yn2. Something like this. It's a vector with two elements. And if we have the plane of yn1 is, well, A, and the plane of yn2 we know is equal to B, then, for example, we have the probability limit of yn1 over yn2 is A over B, which is very nice. If you have if they have moments of the thing like expectation of y1 is C and the expectation of yn2 is D, then the expectation of yn1 over yn2, if I write down this now, is equal to CD. And you put that in your homework, and it's checked by me. I use my red pencil and I say, no, this is not the case. But for claims it does work. That's the continuous mapping theorem. If you have the plane of the argument, you take function, that's the same of taking the function and then the probability limit. Of course, the probability limits should exist. You can only write this down if these probability limits exist. So when you derive something and you want to find the probability limit of a ratio, whether a numerator is a sum, weighted sum, and the denominator is weighted sum, then you should first compute the prims of all these separate terms. And if you found them and they exist, then you can say, well, then the prim of the whole ratio is the same ratio, and then the random variables replaced by their limits, the probability limits. But very powerful thing. We will use it to compute probability limits. Okay, now we have convergence in distribution, which is the weakest form of convergence. So if the yn, let's make it scalar again, and it has a distribution function fn, and meaning the probability that yn is not exceeding x is fn x. The cumulative distribution function. So we have at minus infinity, short notation for the limit, and at infinity it should converge to 1, and it is non-decreasing. If it's strictly increasing, you can invert it. It's continuous from the right. So, meaning if you have here an f, it goes up, and maybe in this point there is a discontinuity, it goes on like this, and now it goes to 1. Then it's continuous from the right. If you have a point, if you look at points here, you get an f, and if you let them converge to this point A, then this should be fa. It's not continuous from the left, because because if you do that, you get to this point, which is different from FA. FA is this one. Continues from the right. And now we look at the limit of these fn's, because if I now put an n here, I can increase n, and then I get different distribution function, etc., etc. And suppose if I take point x here, and here I have fn x, that this fn for this particular x converges to fx, a distribution function evaluated in x. And if that holds for all these x's, for this one f, which is a distribution function, well, I should add a comment to that. Let's now say it is a distribution function. Then we are in this context. This holds true for all x. Then we say the random variables for which distribution functions look like this converge to x, for which the CDF looks like this. We say yn converges in distribution to x, or we could say yn is asymptotically distributed with the distribution function f. However, you will find more difficult situations very quickly, in the sense that suppose it looks like this. We have distribution function fn here, and this is 0, and suppose this point is a half. So this an f, and that holds for all n. If I take the limit, that will also be equal to a half. Sequence of half, half, half converges to a half. And now suppose the variance of this distribution gets smaller and smaller. So for a larger n, it looks like this. It goes on and on. Then the limit of this distribution of these functions looks like this. Here we have 0. Here they all converge to 0. Here they all converge to 1. And here they converge to a half. So this will be the limit of these fn's. And this is not a distribution function, because it is not continuous from the right. Here take the limit, go to 0, I get 1. While the actual value of the limit is equal to a half. So it's not continuous from the right. That means it's not a distribution function. So here we say, if these fn's converge to a distribution function, then we have this. Now suppose this happens. Well, then we still say that we leave out this point and we make it just, we look at the distribution function that at 0 the value is this, equal to 1. Then we do have a distribution function, and for almost all x's it's the limit, except for 0, because there the limit is half, and our f has the value 1 there. If the set where these fn's do not converge to f has mesh 0, then we accept. So we could say that f, y, and x converges to the distribution function of a random variable x. So this, not for all x, for almost all x. Possibly with the exception of the set of Lebesgue measure 0. So the length of the measure of all the points is 0. They still say this is the case. Because the probability that your random variable will exactly equal to 0 will be 0. this distribution function. But okay, when I wrote these rules, I didn't want to complicate things too much. Now I do complicate them a little bit on the blackboard. And if you remember, well, this is the result. Where are we? Here we are, 7. So it may happen that you have a complication like this, so then that is not a problematic thing. We still say it converges the distribution to the x variable if these exceptions constitute a set of measure 0. We turn to 8. We will use 8 a lot of times. So we have a random variable xn times zn, say, and we know that Zn has an asymptotic distribution Z, has an asymptotic distribution, namely the distribution of the random variable Z. So we know what happens to this asymptotically. And for the other part, xn is a random variable, but we know it converges in probability to a number. Then this holds true. This one converges to A, Zn converges to random variable Z, the whole thing converges to A times Z. We will use that a lot. For summation, a similar thing holds. It looks a lot like the continuous mapping theorem, but there we talked about convergence in probability, and here we talk about convergence in distribution. We will use 8 a lot. Now we turn to a central limit theorem, the most simple one. There are many central limit theorems, and this one, well, the first law of large numbers, we had Kolmogorov. A more simple version says if you have IID random variables with an expectation that exists, then you have convergence of the average of these random variables to the expectation of one of these random variables. That was formulated by Bernoulli in 1710. And Bernoulli was a family of brothers and nephews. One of them worked here. That's why the mathematics building is called after Bernoulli. But that has not been the Bernoulli who wrote down the law of large numbers. He was in Paris. And the most simple version of the central limit theorem, I think, is due to Laplace. That was a century after that, in 1810, say. He wrote down a thing very similar to what we have here in 9. If you have IID random variables and they have 2 moments, well, the distribution of all of them is the same because they are IID. We have a mean mu and a variance sigma squared. If that is the case, then we can write down this. This is the average of these n random variables with the bar over it, the average, and this is the central limit theorem. And that means that if you look at yn defined by this, divided by sigma, so this sigma squared will become a 1 then the distribution function of that yn, this yn, converges to the cumulative distribution function of the normal, the standard normal. This is the f related to this one, at least if the sigma square is equal to 1. So we have the asymptotic distribution of the sample mean, the average. about the asymptotic distribution, that is a little bit confusing, because if you look at the distribution function of the average, it has a distribution function that converges to a degenerate distribution function. And we know that the probability limit of that average is equal to mu by the law of large numbers. Here we assume a little bit more than with the law of large numbers, because with the law of large numbers we only assume that the mean exists for that limit, but the variance was not needed for. So that may be non-existent. Here we also need the variance. But for the rest, you could apply the law of large numbers to it, and then xn bar for sure would converge almost surely, so definitely in probability to mu. All the probability mass would center around mu. That's to say, if the n increases, it would look like this. And in the end, you have just a step function. So the limit would be this one. And again, we have this point. If they all go to the same point, then this would be this point. But if you look at the it would not be a distribution function, because it should be continuous from the right. If you look at this one, that would be the distribution function of mu. It is equal to mu with probability 1. It's a step function, and you could say this is the asymptotic distribution of x bar. But we have no use for this, because we use all this asymptotic theory to approximate things. We want to use it to approximate the distribution function of x bar. We want to know this, the distribution of x and bar in a finite sample for the n in the sample that we have. But it may be difficult, even if all these x's have the same distribution. The distribution may be a complicated one, and we cannot find this. It's too complicated. So we want to approximate it. So this one looks like this. And approximating it by this, well, that will be rough. That would not be a nice thing. You want to have a shape in it. And you can achieve that shape by looking at the difference. Well, that's not the main thing, because then here we just have something that converges to 0. But then we have a blow-up factor. We blow it up. And the central limit theorem says that now we have normal. And that's good, because then you would use that in practice by saying that xn is distributed approximately, we could say, which is not an official term, but you know what I mean. I use it as an approximation. The normal would mean u, and variance above line is an exact statement that we know the meaning of mathematically. This one we don't, because we don't know what this means approximately. If you write it down, people could ask, what do you mean by this? And the explanation would be, I mean this. Right? So therefore we use this. But we think of this. Whenever you apply it, then you use this. Approximation of the distribution function of the average. so that we don't have the degenerate distribution. Still, we talk about the asymptotic distribution of x and y. So there is a little bit of ambiguity there. We have, so these are the central limit theorem and law of large numbers. The central limit theorem, you mentioned Laplace, you always, they use Kim-Ching for the law of large numbers. Yes, Kim-Ching they also use for the law of large numbers in the version that you have convergence and probability. Actually, it's due to Bernoulli. And for the central limit theorem, this one, they also refer to it as Lindenberg-Levy. Lindenberg-Levy, that's also a name attached for this central limit theorem. You have Moore, you have Lyapunov, you have Lindenberg, Feller, a whole range of them, applicable in different cases. We will also consider another one when we consider the problem of regression, because we can now apply it to regression. If we say we have a model, y is a vector of ones, iota, times a beta with disturbances. And the u's are ui's are IID with the expectation of one of them. Let's take the first one, 0, and the variance sigma squared. Then we could look at the OLS estimator. That would look like this, which is iota prime y, summation of the elements divided by iota prime iota, which is n. It's just the average value of these y's. That would be the OLS estimator of this paper. Beta would just mean the expectation of one of the y's. And you can think here of can we say something about the asymptotic distribution of the beta hat? Beta hat is beta plus the mean of these u's. Beta plus the sample mean of the u's. In the central limit theorem, we should have IID observations, and then we consider the mean of these random variables. We could use this, right? Because if we use the central limit theorem, then it says that the ui's, well, let's say u1 to un, they are IID, the expectation of one of them is 0, variance is sigma square, so by the central limit theorem, and if people talk about these central limit theorem, they also always mean the most simple one, that would be this one. We have that n to the power half of these u bars minus 0. It's asymptotically normally distributed being sigma squared. And this thing over here, if you look at this, here you have u bar, beta hat minus beta. So here you have the asymptotic distribution of beta hat, this beta hat. So we could use the central limit theorem, as it is on the sheet, to derive the asymptotic distribution of the OLS estimator in a regression model. But then the regression should look like this. Explanatory variables as a factor of once. It's only a constant. Now we could think of, let's make it a little bit more realistic, a little bit more different. And I'm going to consider this as x. And then we will do it later, but you will look at the sequence. Here we have a sequence. 1 times u1, 1 times u2, 1 times un, and here we will get x1 times mu1, x2 times mu2, xn times mun. That is the relevant sequence of random variables of which we would like to know something in terms of an asymptotic of this distribution, as we will show afterwards. Well, we can also show it immediately, of course. This is the thing about which we're going to assume something, that it converges, say. And we take it non-stochastic for the moment. Let's say this converges to C, which is a positive number. So that we can indeed invert it. If it would be 0, we could not invert it. If we want to look at the asymptotic distribution of this thing, then this converges to a constant. And then we know by rule 8, particular 1 and 6, that we can handle it. And the first part converges to A, that would be this part, converges to a constant. And here we take the difference. Let's say beta minus is equal to. This converges to a constant, and here we have an average. Can we say something about the asymptotic distribution of this average? Can we say something about how Zn behaves asymptotically? This one asymptotically. Well, it's an average of a sequence that looks like this. And what do we know about this sequence? The elements are independent. Because the u's are independent. As we assume it throughout. But they are not identically distributed. That is to say, the variance of the first element is x1 squared times the variance of u1, which is x1 squared times sigma squared. Here it will be x2 squared times sigma squared. Only if all these x's are equal, we could use the central limit theorem. Then they will be identically distributed. But now the distributions vary. They're not identically distributed. But therefore we cannot use this central limit theorem, because here it says not only independent, but also identically distributed. We cannot use it. So we could use it when there was a factor of 1s here, and now we take a single explanatory variable, and of course the x's vary, and then we cannot use it anymore. So, it's not very powerful in the regression context. We would need other central limit theorems to deal with regression. We're going to do that. We're going to do that today. Break. And let's see if I can finish something for the break. We did do 9, and we continue with 10 after the break. We start again the whole hour.
哦，对，问一下。